what we are going to start talking about today is an introduction to frequency domain or steady state sinusoidal circuit analysis. Okay. So that rather tedious example problem that we worked on Friday during class was an example of analysis in the time domain, and we saw that we had to apply a reasonable amount of calculus and, in my opinion, a terrifying amount of trig in order to analyze even a pretty trivial circuit. Only had 3 elements in it, right? So what we are going to do today is talk about how we convert signals from the time domain into the frequency domain, and then effectively what the rules are for doing our circuit analysis in the frequency domain. Okay. So we spent a very long time Friday showing that if we have a voltage signal Vm cosine omega t plus some phase angle theta v, we can get responses of the form I of t is equal to Im times cosine omega t plus theta I, where these are our time domain signals. Towards the end of that lecture, I showed you all, using Euler's identity, that those time domain signals were simply the real part of the following complex signals: Vm e to the j omega t plus theta v and Im e to the j omega t plus theta I. I want to call this the mixed domain. Okay. So working with these complex representations, we found that we could get the same answer much more quickly than we did using our time domain analysis. What we're going to talk about today is frequency domain signals, okay? Commonly called phasors, all right? So in the frequency domain, electrical engineers have come up with a shorthand notation for representing these signals, okay? And that shorthand notation is simply, we make a complex number containing only the magnitude and only the phase angle, and we suppress or ignore all of the other information. So this is a frequency or phasor domain signal. So if we want to talk about frequency domain analysis, we have to get used to converting from the time domain into the frequency domain. So let's work a couple of simple example problems here. So let's say that I have a voltage V of t is equal to 8 cosine 5t plus 12 degrees volts. And I want to get the frequency domain representation of this voltage. What do I need to do? Keep the magnitude, keep the phase angle, throw the rest away. It's literally that simple, right? So this would look like 8 angle 12 degrees volts in the frequency or phasor domain. Let's say that we had a current I of t is equal to 7 sine 3 pi t minus 13 degrees amps. What would the phasor representation of this current be? Exactly right. So I'm trying to trip you up here, but Carter caught me on it. All right. Our frequency domain signals are based on us having a cosine representation of our time domain function. Okay. So if we want to convert a sine-based signal into the frequency domain, we have to first convert it into a cosine and then go from there. So what would the cosine representation of 7 sine 3 pi t minus 18 degrees be? Or is that 13 degrees, excuse me. How do we convert from sine to cosine? Subtract 90 degrees, okay? So this would look like 7 angle negative 13 minus 90, or negative 103 degrees amps. So if we're going to work in the frequency domain, we always have to start with cosine signals. And that's because the cosine represents the real part of that mixed domain complex representation. All right. Now, let me make something a little bit harder. Let's say that we have a time domain voltage of 4 sine 9t plus 11 degrees plus 5 cosine 9t plus 21 degrees volts. We wanted to represent this in the frequency domain. So we showed on Friday's lecture that adding two sinusoids like this in the time domain was at a minimum a huge pain in the butt, right? Took us a really long time. So I would argue that we should represent each part of this as a frequency domain representation or complex number, and then add those results together, and it'll be the exact same thing as if we had combined them in the time domain and then converted over. So what I'm trying to say here is, instead of combining them in the time domain and then converting to the frequency domain, I say we convert to the frequency domain and then combine them in the frequency domain, and we will literally get the exact same result. Okay. So this would look like four angle, so 11 minus 90 is negative 79 degrees, plus 5 angle 21 degrees. And if I do that math, I get, sorry, don't know what happened there, 5.836 angle negative 21.457. Much easier to do that math in the frequency domain or using complex numbers than it was in the time domain. So are we all comfortable converting from the time domain to the frequency domain? Just get it in terms of cosines and then only keep the magnitudes and the phase angles, okay? So if, as part of our analysis, I ask for your result in the time domain, how do we convert back? Okay. So the first thing is that we need to know what our angular frequency is, okay? So if I give you something like, let's say I have a phasor voltage is 8 angle 14 degrees volts at a frequency of omega is equal to 6 radians per second. My time domain representation of this signal is 8 cosine 6t plus 14 degrees volts, where the magnitude of my phasor voltage is the same as the magnitude of my time domain voltage. The phase angle of my phasor voltage is the same as the phase angle of my time domain voltage. And I have to include that omega that tells me how quickly my signal is oscillating. Okay. So something that I like to ask on exams, and you'll see this if you look at some of the old exams, is I might give you a list of several, excuse me, I might give you a phasor quantity, so a voltage or a current, and then ask you which of the following time domain signals correspond to this particular phasor, okay? So any voltage signal that has a magnitude of 8 volts and a phase angle of 14 degrees would correspond to that 8 angle 14 degrees phasor, right? So I might trip you up and be like, okay, so this would be a correct answer. An alternative would be, let's say, 8 sine 7 pi t plus 104 degrees is also a valid thing, but only when we haven't specified that omega is equal to 6, obviously. Another potential way that I could represent something would be the sum of two sinusoids. So I could say that this would be the same as 5.431 cosine 11t plus 2.135 sine 11t. All of those would be potentially valid correct answers. All right, so we should be comfortable going from the time domain into the frequency domain and from the frequency domain back out to the time domain as well. All right, so let's look at phasor relationships for circuit elements now. All right. So let's say that I have a resistor. For a resistor R, where I have a current I of t flowing through it, and a voltage V of t across it. Okay. Let's say that I have a sinusoidal voltage, Vm cosine omega t plus theta v, and the sinusoidal current Im cosine omega t plus theta I. And I'm going to work for now in the mixed domain, which means I'm going to represent both of these signals with their exponential complex number expression. Since we know that this complex representation contains literally the exact same amount of information as our time domain signal, but it makes our math easy, all right? So, Kennedy, what's the relationship between voltage and current for a resistor? Yeah, V is equal to I times R. Exactly right, just good old Ohm's law. So, if we substitute in our mixed domain representation of our sinusoidal signals, this would look like Vm e to the j omega t plus theta v is equal to R multiplied by Im e to the j omega t plus theta I. Done nothing but simple substitution. Okay. What I'm going to do now is I'm going to split those exponential functions into the product of two exponential functions. So that would give me Vm times e to the j omega t times e to the j theta v is equal to R times Im e to the j omega t times e to the j theta I. Everybody okay with that? Now we can see that both sides of this equation have a common factor of e to the j omega t. So we can suppress that frequency term which just leaves us with Vm e to the j theta v is equal to R times Im e to the j theta I. We are effectively in the frequency domain now, okay? Because the only pieces of information that we have are our magnitudes and our phase angles. So Vm e to the j theta v is literally just our phasor voltage V. And Im e to the j theta I is just our phasor current I. So in the frequency domain, Ohm's law is Ohm's law. I know that that's probably an underwhelming result, but it actually needed to be proved. Okay? We can look at a couple of other things here real quick as well, okay? If we look at that previous step where I have Vm e to the j theta v is equal to R times Im e to the j theta I, those are complex numbers on both sides of that equal sign, right? So that means the magnitude of whatever's on the left-hand side of the equal sign has to equal to the magnitude of whatever's on the right-hand side of the equal sign. And similarly, the phase angle of the left-hand side has to equal the phase angle on the right-hand side. So we can say that Vm, our voltage magnitude, is simply R times Im. And we can use Ohm's law to manipulate this in whatever ways we see fit, which we will do in a little bit. And we can also see that theta V is equal to theta I, which tells us that resistors do not introduce a phase shift in our signal, okay? Let's look at an inductor next. We're going to use those same representations for voltage and current. So what's the relationship between voltage and current in an inductor? And let's stick with the derivative-based relationships because I don't like integrals. Anybody remember this? Okay. V of t is equal to L di by dt. Everybody agree with Carter? I know I do. Okay. So we can substitute in our mixed domain relationships here. So that's going to look like Vm e to the j omega t plus theta v is equal to L times the derivative of Im e to the j omega t plus theta I. Well, if I take the derivative of that mixed domain current, that's the same as multiplying by a factor of j omega L. Right? Because the derivative of Im e to the j omega t plus theta I is j omega Im e to the j omega t plus theta I. So this looks like Vm e to the j omega t e to the j theta v. I'm splitting up that exponential into two terms again. On the right-hand side, I'm going to have j omega, which is what's being multiplied by t in my exponential function. So this is me taking down that coefficient. L times Im e to the j omega t e to the j theta I. Everybody okay with the math that I've done here? Once again, we have that common factor of e to the j omega t that we can suppress on both sides of the equal sign. Leaving us with Vm e to the j theta v is equal to j omega L times Im e to the j theta I. And we're going to take this bit one step further here. Whenever I multiply by j, so let's talk about the right hand side of this expression right now. I have j omega L, which is arguably a rectangular form complex number, multiplied by Im e to the j theta I, which is a polar form complex number, okay? So what I want to do real quick is I want to express that j omega L bit as a polar form complex number so that we can do this math more easily. And really the key part of this is figuring out how to express j by itself as a polar form complex number, because omega and L are just constants that are going to just make that complex number larger, right? So if I come over here to the right-hand side, I'm going to draw something real quick, and it's just a simple complex plane, where this is my real axis, and this is my imaginary axis. If I go out 1 unit in the real direction, this is 1 plus j0, which is the same as 1 e to the j 0 degrees, or 1 angle 90 degrees, excuse me, 0 degrees. Well, if I go 1 unit in the imaginary direction, that's the same as 0 plus j1, or 1 e to the j 90 degrees, or 1 angle 90 degrees. If I went 1 unit in the negative real direction, that's going to look like -1 plus j0, or 1 e to the j 180 degrees, or 1 angle 180 degrees. And technically, I could put a negative sign in front of those 180 degrees things there and still be perfectly correct. And lastly, if I go 1 unit in the negative imaginary direction, this looks like 0 minus j1, which is the same as 1 e to the negative j 90 degrees, or 1 angle negative 90 degrees. So if I'm multiplying the right-hand side of this expression by j, that's me multiplying it by 1 angle positive 90 degrees, which means that I could rewrite this as omega L Im e to the j theta I plus 90 degrees. All right, so our left-hand representation, we have Vm e to the j theta v. So that is purely a phasor quantity because we only have a magnitude and we only have a phase angle. That's my phasor voltage V. My middle representation looks like j omega L times my phasor current, because my current is just I with a phase angle of theta I. So this is my phasor relationship. Now, if we look at the left-hand representation and the right-hand representation, what we can see is that the magnitude of my phasor voltage is simply omega L times Im. And the phase angle of my phasor voltage is theta I plus 90 degrees. So what that means is that the voltage drop across an inductor is always leading the current by exactly 90 degrees. We'll do experiments in a couple of days that will literally prove this. All right, any questions on our inductor relationship? I'm going to start putting a box around the important stuff. All right. So let's say this relationship here, pretty important. These two here, also important. And I'll do it for my resistor ones as well. All right. So our last circuit element that we're going to develop phasor relationships for is the capacitor. Pardon? For the resistor, just V is equal to R times I, and then the relationship between the magnitudes and the phase angles, and the exact same quantities for the inductor. All right. For a capacitor C. So what's the derivative-based relationship between capacitor current and capacitor voltage? Absolutely right, Connor. Our current I is equal to C times the derivative of our voltage with respect to time. So if we substitute in our relationship here, and now that we know effectively what taking the derivative of this exponential representation looks like, what we're going to have is Im e to the j omega t e to the j theta I is equal to j omega c Vm e to the j omega t e to the j theta v. I'm going to suppress my frequency terms, leaving me with Im e to the j theta I is equal to j omega c Vm e to the j theta v, which is the same as omega c Vm e to the j theta v plus 90 degrees. So I'm just taking a couple of brief shortcuts here because this is so similar to what we just worked out a moment ago with inductors. All right. So on the left-hand side, this is my phasor current I. In the middle, we have a quantity of j omega c times my phasor voltage V. And if we look at the left-hand representation and the right-hand representation, we can see that Im is equal to omega c Vm and theta I is equal to theta V plus 90 degrees, which means for a capacitor, the current leads the voltage by exactly 90 degrees. So we have just developed our frequency domain relationships So our voltage and current relationships for resistors, inductors, and capacitors for steady state sinusoidal circuits. The next topic that I'm going to talk about is the concept of impedance. Okay. So impedance is, in the frequency domain, what resistance is for DC circuits. So let me explain that real quick. Way back at the beginning of this class, literally months ago at this point, we said that if we have a black box network and we apply some voltage Vs across the terminals of this network, if we measure this voltage V test and we measure this current I test, the resistance of our network was simply V test over I test. I literally had you guys do an experiment to prove this. Second day of class. Well, in the frequency domain, if we take a linear black box network, and we apply a phasor voltage and we measure a phasor voltage V test across the terminals of our network and measure a phasor current I test flowing through our network, the ratio of the phasor voltage to the phasor current is what's known as impedance. So impedance plays the role of resistance in the frequency domain. Now, because impedance Z is a ratio of complex numbers, the impedance in and of itself must be a complex number, which we can express in either a polar form or a rectangular form. Okay? So if this is Vm angle theta V divided by Im angle theta I, then that looks like Vm over Im angle theta V minus theta I, or the magnitude of Z angle theta Z. Right? This is our polar form representation. I believe it's reasonably straightforward. Okay. Our rectangular form representation is given by R plus J X, where R the resistance is the real part of Z, and X the reactance is the imaginary part of Z. So let's determine now the impedances of resistors, inductors, and capacitors. So go back in your notes, one page or whatever, and look at our phasor relationship for resistors, right? It said that V is equal, phasor voltage V is equal to phasor current I multiplied by R. So if I divide both sides of that expression by my phasor current I, that gives me my impedance. And so from that, the impedance of a resistor, V over I, is literally just the resistor value itself, which, as a polar form complex number, looks like R angle 0 degrees. And as a rectangular form complex number, looks like R plus J 0. Not degrees here, sorry. So the real part of our impedance is literally just the resistance that we've been dealing with for the entire duration of this class. Not remotely a new concept whatsoever, okay? Let's look at an inductor. The ratio of the phasor voltage to the phasor current for an inductor is simply J omega L. Which looks like omega L angle 90 degrees for a polar form representation, and 0 plus J omega L as a rectangular form representation. So the impedance of an inductor is purely imaginary. So we say that inductors have positive reactance. Now, before we move along to capacitors, I want to look at the units of this thing here, okay? The units of omega are expressed in radians per second. And the units of inductance is the Henry, which is dimensionally the same as a volt second per ampere. So we have radians, which is a dimensionless quantity, divided by seconds, being multiplied by volt second per ampere. And so what happens is the seconds cancel each other out, and we are left with volts per ampere, which is more commonly known as an ohm. So the impedance of an inductor is measured in ohms. All right. Another interesting thing here, real quick, the impedance of an inductor is frequency dependent because it depends on omega, right? So what does the impedance of an inductor simplify to when omega is equal to 0, which would correspond to a DC circuit? 0. So this matches up still with everything that we've learned about the concept of inductance, right? It's interesting to observe here that as the frequency increases, the impedance increases as well, because it's a simple proportional relationship, right? So at very low frequencies, inductors look like short circuits, and at very high frequencies, inductors start to look like open circuits. If we look at a capacitor, I shouldn't have that line there. The ratio of our phasor voltage to phasor current is 1 over J omega C, which looks like 1 over omega C angle negative 90 degrees, or 0 minus J over omega C as a rectangular form complex number. So to be clear here, I am saying that 1 over J looks like negative J, which I believe we proved in our complex number lectures. Okay, so that's where that negative sign comes from. Dimensionally, we have 1 over radians per second being multiplied by farads, which are amp seconds per volts. Our per second cancels out our second, and we are left with the reciprocal of amps per volts, which is an ohm. A capacitor exhibits only negative reactance, so it's purely its impedance is purely imaginary as well. It's got negative reactance. At very low frequencies, because of the inverse relationship between frequency and impedance for a capacitor. So at very low frequencies, our capacitors look like open circuits, and at very high frequencies, they simplify to short circuits. So since the units of the impedance of resistance, the impedance of inductances, and the impedance of capacitances are all the same, ohms, that means that we can treat impedances in frequency domain circuits like resistors in DC circuits. What that means is we no longer have to memorize different rules for how to combine our elements. Everything combines like resistors in the frequency domain, as long as we're dealing with impedances, okay? So I can have capacitors in series with inductors, all that kind of good stuff, and just lump it all together into a single equivalent impedance. So let's see, it's 3:20. I've got an hour left. All right, so let's use these impedance relationships and talk about actually solving circuits in the frequency domain. So I don't have my notes from Friday in front of me. Could you guys tell me what the circuit was that we analyzed? I want to say it was a voltage source. Thank you. 8 ohms, 50 millifarad. And what was the voltage source voltage? 12 cosine 5t plus 10 degrees volts. Thank you, Scholar. All right. So this is our circuit in the time domain. And we were interested in finding this quantity, a time domain current I of t, right? That's what we tried to do. Or I guess technically we accomplished on Friday after roughly 20 plus minutes of math. All right. So if we want to analyze a circuit in the frequency domain, our first step is going to be to convert the circuit to the frequency domain. Okay. So what that means is I'm going to replace my time domain voltage with a phasor domain voltage. And then I'm going to replace my resistor and capacitor here. I don't know why I drew it as a resistor up here, with their impedances, right? So, McKinley, how do I convert that voltage, Vs of t is equal to 12 cosine 5t plus 10 degrees into a phasor domain voltage or phasor voltage? 12. So I keep the magnitude, angle 10. That's exactly right. 12 angle 10 degrees volts. So that is my phasor representation of that voltage. And this current, I with a bar over it, is a phasor representation of the unknown quantity I'm trying to solve for. Okay. Abby, how do I convert my 8 ohm resistor into the frequency domain? So what's the impedance of my resistor? So just R. So the resistor doesn't change at all. So if it was an 8 ohm resistor, it continues to be an 8 ohm resistor. Okay. Kai, what do I do with my capacitor? So how do I convert my capacitor from the frequency, excuse me, from the time domain to the frequency domain? So it's a capacitor. All right, so negative J over omega C. All right. So what's omega? I'm sorry. I disagree. 5, yes. So omega is 5 radians per second. And C is obviously 50 millifarads. So if I put 1 over 5 times 50 times 10 to the minus 3, this is going to look like negative J4 ohms. So if I wanted to get that current I, phasor quantity there, I could say, using basic circuit analysis techniques here, that this is simply 12 angle 0 degrees volts divided by those two resistors in parallel. Oh, angle 10 degrees, thank you. Angle 10 degrees volts divided by the equivalent impedance of that 8 ohm resistor in parallel with that negative J4 ohm capacitor, right? So that's going to look like 8 times minus J4 over 8 minus J4 ohms. For your calculator and stuff, you literally have to use, so you would have to do I instead of J because I don't think your calculator has a J button. The point here is, let me write down this answer, 3.354 angle 73.435 degrees amps is that we get the exact same result as we got with tons and tons of calculus and trig using literally a single step of elementary circuit analysis, okay? Yes, ma'am.
Can you explain how you got the
Sure. So omega is 5 because omega is the bit that's multiplied by the t inside of the cosine argument. And 50 millifarads is 0.05. So 5 times 0.05 is 0.25, and then 1 over 0.25 is 4. Yep. Connor.
Is it easier to represent the impedance of capacitor as a negative J omega C angle negative 90?
Whatever floats your boat. Typically speaking, I say that ZC is 1 over J omega C, but that's still going to be the exact same thing as negative J4, which that is identical to 4 angle negative 90 if you want to put it at that. I don't particularly have a preference as to whether or not you guys choose to express your quantities in polar form or rectangular form. I will say personally, voltages and currents will always be in polar form for me. Like that's what I'm going to give them to you as and all that kind of good stuff. With regards to impedance, whatever's more convenient is fine by me. Sometimes I express them as rectangular numbers, other times I express them as polar form numbers. Just whatever floats my boat at any given moment. Voltages and currents, I 99.9% of the time express in terms of polar form complex numbers. So when we are analyzing a circuit in the frequency domain, literally all of our DC circuit analysis techniques are fair game, okay? So we did this effectively just using Ohm's law and simple impedance combination, which came about because of KVL, I think. KVL or KCL, doesn't matter, right? We could do things like current division, voltage division, source transformation, nodal, mesh, superposition, Thevenin and Norton equivalent circuits. Literally all of our DC circuit analysis that we learned over the first 3 to 3.5-ish weeks of this class are all back now. The only wrinkle is that they use complex number relationships. Everything else is literally exactly the same. Now, your calculators, every single one of them, regardless of how cheap it is or how expensive it was, is incapable of solving a system of equations that have complex numbers. Okay. So what that means is that on your exams, you're likely going to have to rely on techniques like superposition and source transformation and things like that in order to simplify circuits to get them to a manageable form. Okay, so this last third of the class is really going to drive home a lot of those exam 1 relationships that maybe you're not super familiar with. Okay? So let me talk about what I mean. Let's say, and I'm just going to start with a circuit in the frequency domain here. I have 12 angle 40 degrees volts. A generic impedance, I'm going to call it ZA. That is 5 plus J2 ohms. A current source, that is 1 angle negative 30 degrees amps. An impedance, which I'm going to call ZB. That will be 11 angle 15 degrees ohms. An impedance over here, which I'm going to call ZC. That will have a value of let's call this 9 minus J 15. Oh, I want to know what the phasor voltage drop over my current source is. Now, I know some of you see two meshes and therefore say mesh. I'm going to remind you, the calculator can't do it. So how can we go about determining this quantity without relying on the crutch that is mesh analysis that so many of you lean upon? So Connor suggested that we could do superposition. I agree. That is one of a plethora of different methods that we could utilize here. Okay. So let's work this problem using superposition. Just real quick here. And while I'm at it, I'm going to make a copy of this because we're going to work this guide literally just a couple of different ways. Just to show you that all of our DC analysis techniques are fair game. Okay. So using superposition, let's say with the voltage source on and our current source off, this is going to look like this guy. 12 angle 40 degrees. Here's the A. Here's my voltage source, VCS prime. Here's ZB. Here's ZC. What can I do to determine the value of this voltage drop VCS prime? Abigail, you have any thoughts? KCL wouldn't give us a whole heck of a lot of information. KVL is a possibility, but I would argue, so if we did KVL around that loop, we could find the current that's flowing in the loop and then multiply that current by ZB plus ZC to get the voltage drop. That's absolutely one way that we could do it using effectively just KVL and Ohm's law, but I would like to be slightly lazier. Voltage division. Because we have a known voltage drop and then the three impedances in series, and we just want the drop over some of the impedances, right? So I would argue that this is just going to be 12 angle 40 degrees volts times ZB plus ZC over ZA plus ZB plus ZC. Does that make sense? So let's take a moment. Throw this in our calculator. By the way, I would highly implore you all to learn how to store things in your calculator. Like I'm going to store impedance ZA as A and impedance ZB as B and impedance ZC as C because I know that I'm going to have to use them over and over and over again. So I got 11.010. Sorry, I wrote that poorly. 010 with an angle of 20.051 degrees. Volt. And I'm going to put out here in red a little X to remind me of what I stored that in my calculator as. Anybody else get that result? All right. So with our voltage source off and current source on, our circuit's going to look like this. That was one angle negative 30. Call this VCS double prime. So I need to put another prime on there. All right, so Mo, how do you think we could go about solving for this voltage? Sorry, Chaw, did you have your hand raised and I ignore you? All right, let's look here. I think I put 5 plus J7, but that might supposed to be 5 plus J2. Okay, sorry. Let's go. So let me write better. Let's call that a 2. Let me update 5 plus 2I. Store that as A. And then $10.399 with an angle of 30.638. All right, so was it calculator error? That was, my handwriting was not legible enough, so I apologize for that. All right. So back to my original question, Mo, how might we go about solving for this quantity VCS double play? Pardon? No, there's absolutely no reason to do mesh right here. So let me explain what I mean by that, all right? We have a current source in parallel with an impedance to the left, in parallel with an impedance to the right, and we just want the voltage drop. So why can't we say that voltage is just that current times those impedances in parallel, right? So VCS double prime is going to be one angle negative 30 degrees amps times ZA in parallel with ZB plus ZC. So it's going to look like ZA times ZB plus ZC over ZA plus ZB plus ZC. Where, just to be clear here, that's what this represents, right? Mesh is off the table because our calculators literally can't solve that system. Okay, so we have to be creative here. So I get 4.667 with an angle of negative 17.560 degrees. Anybody confirm this? All right. So using these results, the voltage drop across my current source with both sources on at the same time, which is what I'm looking for, is just adding those two guys together. So for me, that's what I have stored in my calculator as X plus what I have stored in my calculator as Y. And so I get 14.980 angle 9.091. Let me make sure that I stored that other thing as X correctly earlier because I don't think that I did. Yep, I absolutely didn't. Let me fix these. Sorry. 13.951 angle 16.198. Can anybody confirm this? All right. So we use superposition, and in a couple of steps, so superposition and then Kirchhoff's, superposition, and then after using superposition, we had to use Ohm's law and voltage division. We were able to get the results. Okay, let's take another crack at this problem using a different method. So Joel, how do you want to take a stab at this that isn't relying on superposition? Source transformation, absolutely. So since I'm trying to find the voltage drop over the current source, I'm going to leave the current source where it is. All right. So I'm going to do a source transformation on the practical voltage source that's formed between the 12 angle 40 degrees voltage source and the 5 plus J. I can't remember if this is a 2 or a 7. Apparently I saved it before I made it more legible. 2. All right. Thank you. 5 plus J2 ohm impedance. So that's going to look like a current source over here on the left in parallel with ZA, in parallel with our one angle negative 30 degrees amps current source, in parallel with a combination of ZB in series with ZC. So how do I do current division? What's the value of that current supposed to be? Obviously, I'm not going to ask you to do that in your head, but you know, how would I go about getting it? Yeah, so it's just the voltage divided by the impedance in this case, right? So 12 angle 40 over 5 plus J2. Which I get to be 2.228 with an angle of 18.199 degrees. Amps. We're looking for this quantity here. So how do we get it? You need to add them because they're in the same direction, right? So when we do source transformation, we disconnect and then we reconnect. Because these current sources are in parallel and both of their directions are up, because the positive polarity terminal is on top, they will combine together. They add, not subtract. Only when they're in opposite directions do we do a subtraction operation here. So let's prove it. Right? So I would say that this quantity, VCS, is simply 2.228 angle 18.199 amps plus 1 angle negative 30 degrees amps multiplied by ZA times ZB plus ZC over ZA plus ZB plus ZC. All I'm doing here is applying Ohm's law. So I'm saying the total current is being multiplied by the equivalent impedance. I get 13.951 angle 16.198 degrees. Which, if I'm not mistaken, is the exact same thing we got using that entirely different analysis method. All right, I want to work this problem one last way because it's something that probably a lot of you wouldn't think about. And then I'm going to stop talking, which I'm sure you're all very ready for. I promise there's a method to my madness. Okay. I can't get this thing lined up how I want it. All right. So I have to fix this yet again. All right. So I told you all earlier that we can't use our calculators to solve a system of equations that have complex numbers. But if I can get one equation and one unknown, I can do algebra to get the circuit in a place where I can analyze it using my calculator. So what I am going to suggest is we're going to treat this bottom node as ground. And we're going to solve for this nodal voltage VCS. Is this what one of you guys were suggesting? Yeah, absolutely. Okay. This is fair game, but it does require a relatively annoying amount of algebra to get it to where a calculator can do it. Okay. So if I apply KCL at this top middle node, I'm going to have VCS minus 12 angle 40 degrees volts divided by ZA minus 1 angle negative 30 degrees amps plus VCS over ZB plus ZC is equal to 0, where I'm lumping those two impedances together as a single impedance so that I can get rid of that extra node that would prevent me from having a one equation, one unknown system. Okay. From here, this looks like VCS times 1 over ZA plus 1 over ZB plus ZC is equal to 12 angle 40 degrees volts over ZA plus 1 angle negative 30 degrees amps. Now, when I divide by 1 over ZA plus 1 over ZB plus ZC, that is the exact same thing as me multiplying by ZA times ZB plus ZC over ZA plus ZB plus ZC. Effectively, the equivalent impedance of those two branches in parallel. So this gives me VCS is 12 angle 40 degrees volts over ZA plus 1 angle negative 30 degrees amps, all multiplied by ZA times ZB plus ZC over ZA plus ZB plus ZC. This expression is literally the exact same expression that we got doing a source transformation, 100%, where 12 angle 40 over ZA represents that current source on the left-hand side. So the results of this are obviously the exact same thing as what we just got, because we wound up with literally the exact same equation. All right, so that's enough out of me for today, unless anybody has any questions or anything. Got an in-class assignment and all that kind of good stuff. If you have any questions, I'd be happy to answer. Bad. Technically number 20. So number 19, you should have been able to do pretty much everything except for one thing. I don't know that I remembered to open it, so I'm just going to have them both do, let's call it Wednesday or something like that.